For my topic, I'm going to be talking about understanding cyclical clock arithmetic and barcodes. In our everyday lives, we use clock arithmetic without even realizing it. Clock arithmetic is the arithmetic where we return to 1 after counting to 12. We use it when we are reading clocks, and in some ways it can be more simple because the numbers never get too big. Unlike regular numbers, a clock cycles around in 12 hours and then returns to its original position. Clock arithmetic can also be referred to as modular arithmetic. In regular math, the solution to this problem would turn out differently, but in clock arithmetic, we count a different way. The first step is to multiply the first numbers. 4 times 7 is equal to 28, but using clock arithmetic, 28 equals 12 plus 12 plus 4. This is because we're counting up to 12, and then we are brought back to 1. With the next number being 12, you are left with the number of 4. Now, 20 is equal to 8 because 20 equals 12 plus 8. This is the same procedure. After 12, you start back at 1, so the number is 8. The final answer turns out to be 4 times 7 plus 20 equals 4 plus 8 equals 12. So the final answer according to this arithmetic is 12. As we look at these cycles of 12, we develop an idea of equivalence. The notion of equivalence in clock arithmetic is 48 being equal to 12. This is because if we did regular math to figure out 4 times 7 plus 20, we would get 48. Using clock arithmetic, we get 12, which means 48 is equivalent to 12. The next topic I am going to be talking about is barcodes. Barcodes often use the same arithmetic as clocks because they are often made up of 12 or 13 digits that make up their universal product code. The first 6 digits of a barcode on a product has encoded information about the manufacturer. The next 5 digits encode information about the specific product. This leaves us with one leftover number, which is referred to as the check digit. The check digit is used to provide a way to detect if a universal product code number is incorrect. When using the check digit with 12 digits, you first line up the first 11 digits of the universal product code number. First, set up the digits in a sequence. Next, you combine the numbers in a unique way by multiplying every other number by 3, and then adding them all up. An example scenario is using the barcode on a Kleenex box. Say someone calls the number for Kleenex and recites the barcode, and you're a representative of Kleenex and you want to confirm that it is accurate. You can confirm that it is correct using the check digit. They recite the barcode, so you plug it into the formula. When plugging it into the formula, you add the check digit, for example, C. When you add the preceding sum of C, you get an answer that is evenly divided by 10. Here is another way to write this problem out. Going back to modular arithmetic, 10 is equivalent to 0, so this means that the check digit should equal 9. Since 1 plus 9 equals 10, the last digit of the code is 9. Computing the sum results in this equation. This equation shows the sum is not equivalent to 10, so there must have been an error with the code. Using the check digit system, if an error is made, it will always be detected. Most people would not think that there is a deep and powerful number theory when they look at a clock or barcode. Many people may have never heard of modular arithmetic, but we use it every day without difficulty. Modular arithmetic models the cyclic nature and the ideas of cycles in our daily lives. Our world contains many examples of cycles, the seasons, phases of the moon, birth and death, and more. I enjoyed learning about this topic and found it interesting how it is used in everyday life. I did not realize that modular arithmetic could be used for other things besides clocks. I also never knew the reasoning behind barcode numbers until now. I also learned that the check digit system can be used for checking errors in data. Overall, both of these mathematical topics are useful tools to understand in everyday life.